All right, today we're going to tackle one of the wildest, most profound ideas in all of physics, quantum entanglement. And trust me, this is a concept that's going to challenge everything you think you know about how reality works. So let's just dive right in and see what this is all about.
And if you think you're going to be confused, get this. Even Albert Einstein couldn't wrap his head around it. He was so bothered by the whole thing, he gave it this famous nickname, spooky action at a distance. I mean, why? Because it looked like it completely shattered the #1 rule of his own theories, the speed of light. So what on earth could make the great Einstein so uncomfortable?
Okay, so the problem, the real drama here, comes down to a major clash between the two heavyweights of modern physics. In one corner, you've got Einstein's relativity, the theory that governs the huge stuff, planets, galaxies, the whole cosmic dance. And in the other corner, you've got quantum mechanics, which is perfect for describing this super tiny stuff, atoms and particles. And here's the kicker, they just don't play by the same rules at all.
And this really gets to the heart of the fight. See, relativity's world is, well, it's pretty intuitive, right? Nothing goes faster than light. Things are where they are. But the quantum world, it's a whole different ballgame. It says, hey, maybe things can be connected instantly over vast distances, and maybe a particle doesn't even have a property until you look at it. It's all about probabilities. You can see how these two views they don't seem like they can both be true at the same time.
So what is this spooky thing? What is entanglement really? Let's break it down.
Okay, here's the core idea. Imagine you have two particles that are linked up, they're entangled. From that moment on, they stop being two separate things and start acting like a single unified system. They're connected. So no matter how far apart they get, if you measure one, you instantly know the state of the other. Instantly.
Right now, your brain is probably screaming, that's impossible. That breaks the speed of light. And you're right, it sounds like it should. So to see why it doesn't, we need a little thought experiment. This is where things get really cool, but also where we find the catch. All right, let's picture this. We've got our two entangled particles. Let's say we're measuring their spin, which can either be up or down. Now, we take one of these particles and send it off to a lab in Manila.
And just to make things interesting, we'll send the other one all the way to Mars. We're talking millions and millions of miles apart.
Okay, here's the moment of truth. The scientist in Manila measures their particle, and it's spin up. So the question is, what's the spin of that particle way out on Mars?
Well, the very instant that measurement happens in Manila, the Mars particle becomes spin down. Not a few minutes later, not after a signal could have traveled there, instantaneously. Bam. It just is.
So, does this mean we can send messages faster than light? Can we build a quantum communicator like in science fiction and have instant chats with a Mars colony? This is the million-dollar question.
And the answer, which might be a little disappointing, is no, you can't. And the reason why is so clever.
See, it all comes down to control, or really, the lack of it. The scientists in Manila can't force their particle to be up to send a 1 or down to send a 0. The result they get is totally random. It's a 50-50 coin flip every single time. So they just see a random string of ups and downs. And the scientists on Mars, they also see a totally random string. The only way they know something amazing happened is if they get on the good old-fashioned radio, which travels at the speed of light, and compare notes. Only then do they see that their random strings are perfectly inversely correlated. So yeah, no usable information actually traveled faster than light.
Okay, so if it's not a secret telephone line, what in the world is entanglement? What's actually happening? Well, the real answer isn't some invisible string connecting the particles. The answer, it's in the math.
Don't worry, we're not going to do a ton of equations, but we need this one concept. You have to think about where a quantum state lives. It's not in our regular 3D world. It's described in a kind of abstract map of possibilities called a Hilbert space. Just think of it as the language we use to describe quantum reality.
And here's how it works. A single particle? Easy. It has its own little description in this Hilbert space. Two separate particles that haven't interacted? Also easy. You just describe one, and then you describe the other. They're independent. But the moment two particles become entangled, something amazing happens in the math. You can no longer describe them separately. Their combined state becomes a single mathematical description, a single wave function. They are, mathematically, one thing.
And that's it. That's the big reveal. This mathematical fact,
the inability to separate them into two different equations, that is entanglement. It's not a force pulling on them, it's a property of the system as a whole. They were never really two separate things to begin with.
Which leads to this really deep idea. The information in an entangled system isn't stored in particle A or particle B. The information is stored in the relationship between them. The connection is the information.
This completely flips our normal way of thinking on its head. Classically, you think the whole is just the sum of its parts, right? You understand the bricks, you understand the wall. But the quantum view says, nope, the system is the fundamental thing, and the parts only make sense in the context of that whole system.
So, let's zoom out. What does this tell us about the universe we live in? Well, it's pointing to a reality that is way, way more connected than we ever thought possible.
And here's another mind-blower. We tend to think entanglement is some weird, exotic thing that only happens in a physics lab. But it's not. It's the default. Anytime two quantum particles bump into each other, entanglement is the most likely thing to happen. It's happening everywhere, all the time.
And that leads to this incredible conclusion. Our entire experience is based on the idea of separate things. A chair, a table, you, me. We think separability is the default, but the math is telling us that connection is the default, and true, complete separation is actually the weird, special case.
What this shows us is that our everyday view of the world is really just a convenient illusion that works for big objects like us. But when you get down to the fundamental fabric of reality, it's all woven together by these deep, strange, non-local connections. We are staring into the face of a completely new kind of reality.
So I'll leave you with this question to chew on. We build our lives, our science, our philosophy on the idea of individual, separate things. But what if that's not the fundamental truth? What if the universe isn't a collection of tiny separate bits, but a single, profoundly interconnected whole? What does that change?